Now we're going to use the results of our pressure distribution in a static fluid to analyze the forces on a submerged surface. This could be such as like a hatch on a submarine, something like that. You might want to know how much force it's going to take to open that up, or if there's a little valve on the side of a fish tank, you might want to know how much force you're going to need to design that valve, so that you know how to design it so you can open it easily and things like that. So we will be doing both planar and curved surfaces, but first we were going to do planar surfaces here. And what I mean by a planar surface is that the submerged object is planar. Now, its cross-sectional shape, if I'm looking at it from the side like this, it may be some sort of crazy shape, but if you're looking at it from the side, it forms a perfectly straight plane. And so the geometry here is that we have the surface of the water here. It doesn't have to be water, but it's usually water. It's at atmospheric pressure. Remember, that's what the triangle with the three little lines means. We have a thin hatch over here, and essentially what we're going to do is we're going to integrate the pressure forces acting on the surface of this hatch to find the net force on the hatch. Okay, and so we're going to assume that the hatch makes an angle theta with respect to the horizontal. And we're going to call the depth h, and we're going to call y the distance along the surface to a given point. Okay, and so y will be this distance here, which is the same as this distance here. Okay? And so now what we're going to find is the net resultant force due to the fluid pressure pushing on this gate. So what is the resultant force? And a lot of times you care about the moment that pressure is producing on this object. And the reason there's a moment that is produced is because the pressure is higher on the bottom of the surface than on the top. And so there's going to be more force pushing over here than there is over here. And so there's going to be a net moment. And so then where do you put this resultant force to produce that exact same moment? Okay, and so how we go about doing this is we actually integrate the pressure forces that are on the surface of the object. And so if we look at a view of the gate from the top and rather than from the side, the picture will look something like this. So again, we have G going straight down, and this is the surface here. And so we want to integrate the pressure acting on this. And so the distribution of the pressure forces will be like this. And this is just nothing more than a classical distributed load that you guys would do in statics. So what we have to do here is, and we know the distribution of this pressure because we know that the pressure in this water is just a function of the depth h. Okay? And so basically all we need to do to find the net force, or the resultant force I should say, is basically find the amount of force in the small differential patch of area dA. Okay? And so we know that the force on this little patch is just the pressure on that little patch times the area. And then if we want to find the resultant force, we just integrate all the forces on all these little differential patches. Okay? And so that's essentially what we do. So now we know from the previous result that the pressure equals the atmospheric pressure on the top plus rho g h. Okay, remember here, h is the depth, not y. Y is the distance along the surface. Okay, but we can use a bit of trig here that we know y is that distance here, h is this distance here, and we know theta. And so h is just nothing but y times sine of theta. Okay? So I can take this definition for h and substitute it into our pressure distribution. So now I know pressure as a function of y and not necessarily as a function of h. Okay, and the reason that we do this will become more clear after we do when we start doing moments, and this actually turns out to be really nice when it's said and done. Okay, and so we substitute that in, and we get P equals the atmospheric pressure plus rho g y sine of theta. Okay. Now, we know then that delta F in this little patch is just nothing more than P times the area of this little patch. And so to find the resultant force, we just integrate P dA. So that's the integral over the area of all the delta F's, and that is equal to the integral of P dA over the area, over the entire area of this object. Okay, and so we then just substitute this expression here, and we get this equals the integral over the area of P naught, or the atmospheric pressure, dA, plus the integral over the area of rho g sine theta y dA. And we're going to assume that basically rho and g and sine theta are constant. Well, theta has to be constant because we're assuming a planar surface. So we're going to assume constant. Okay, and also we've implicitly assumed that both rho and g are constant just by how we define the pressure variation with depth. The results I'm going to show you in this section, we are assuming that rho and g are both constant. If they are not constant, then you basically will always have to integrate the distributed pressure load every single time. Okay? So, anyways, we substitute that in, and we can now pull these terms out of the integral because they're constant. Then this equals P naught, that's just constant, times the area, because the integral of dA, because the integral over the area of dA is just equal to the area by definition. So then we got rho g sine theta, the integral over the area of y dA. Okay? But the integral of y dA equals the y value of the centroid times the area. This is something you guys used in statics. So this yc here is just the y position, of the centroid. Of the hatch. Okay? So basically, say if the centroid of this object is here, basically yc is just the distance along the surface to the centroid. So basically yc would be here if this point is the centroid. Okay? So then this equals P naught times the area times, or plus I should say, rho g yc sine theta times the area. Okay, well, yc sine theta is just the depth hc at the centroid of the surface. And to see that, we can say, well, if we sort of trace the centroid point up, that would be right here. And so yc is the distance from here to here, and hc is just the depth of the fluid at that point. Okay, because that's just yc sine theta. Okay, So that's the resultant force. So I'm gonna collect the A, and we can find that that the resultant force is equal to P naught times area plus rho G H times the depth at the centroid of the object times the area. And that equals P naught, which is the atmospheric pressure, P naught plus rho G HC times the area. Well, remember our distribution of the pressure is P naught plus rho G times H. Here we have P naught plus rho G times the height at the centroid. So this term here is nothing more than PC, the pressure at the centroid of the hatch. Okay, and so this equals PC times the area. Okay, and so this is a really nice result, because it basically means that the resultant force on the gate, if rho and G are constant, is nothing more than the pressure evaluated at the centroid of the submerged gate times the gate area. That's it. You just need to find the pressure. So you just need to find the centroid, then find the pressure at that depth, and then multiply that by the area. And that's and when you do that, you have the resultant force. Now there is an assumption here, and not only does rho and G have to be constant for this to work. If not, you have to do very formal integrals. But this also only takes pressure on one side of the gate into account. But more often than not, for instance, if this is the side of a tank here, there will be a pressure loading on the back too. But oftentimes that's just air, and so that's nothing more than the atmospheric pressure, an almost uniform load of atmospheric pressure pushing on the back. Okay, and so basically don't forget that this analysis only considered one side. And sometimes you'll have different fluids on both sides, and so you need to consider the loading on both sides. Okay? So now we know the resultant force pushing on the gate. Now we need to know, we know the resultant force. Now we need to know, where do we put this resultant force on the gate so that the same moment is produced? Okay, so we can use that information to tell us where to put the resultant force. Okay. Okay, and so now to do that, we basically look at the geometry again, where again we have our little submerged hatch here, and we are replacing a distributed pressure loading with a single point load, right? And you know, in statics, you can convert one to the other. And so, as I said, this distributed pressure force will produce a moment about the origin, which is right there at the surface, and the net moment about the surface is just nothing more than the integral of all the moments on the surface on all of these little strips about the origin. Okay, and so on each strip we will have a small delta moment y about the origin, and that will equal to y, which is the moment arm to this to that line, times the force, which is just the small delta f on this patch. Oops, the small delta f on this patch. And we know that that's just y times p dA. And then the net moment is found by just integrating all the by by basically integrating all of the moments about the origin on these thin little strips. Okay, and so this implies that the net moment about the origin is equal to the integral over the area of all the small differential moments, and that's equal to the integral of the area, because we know that the differential moments are nothing more than y times p dA. And also defining y in this way actually makes this analysis quite a bit easier, which is why we did that. Okay, so that equals the integral of y times the pressure dA. Well, we can use our expression for the hydrostatic pressure of variation. So this equals the integral over the area of y times the atmospheric pressure plus rho g y sine theta dA. And just recall that y sine theta is just nothing more than h, which is the depth. Okay, but we have a y here and a y here, so we will leave that in terms of y rather than h. Okay, so we're going to start to work with this integral a little bit. So then this gives us that the net moment is equal to P naught, because, well, atmospheric pressure is constant. We can yank that out. P naught and times the integral over the area of y dA plus the integral over the area, and I'm going to pull out of the second integral here, I'm going to pull out the rho g sine theta plus, plus rho g sine theta, because we're assuming all of those are constant. Rho g sine theta times the integral over the area of what's left, so that would be y times this y here, of y squared dA. Okay, well, we already know what this term is here. This here is just the y value of the centroid times the area, which we defined above, and that's just a result from your statics. And the integral of y squared is the second moment of inertia about the free surface. So this is the second moment of inertia about the free surface. And that would be Ixx. Okay, and so this is just the moment of inertia about the axis. So for if you remember in statics, in mechanics of materials, you dealt with that all the time. For a rectangle, it's 1/12 bh cubed. It's basically that. Okay, and so we then use those definitions. So this is nothing more. The first term is nothing more than the atmospheric pressure times the y value of the centroid times the area of the gate. And we add the second term to it, and that's rho g sine theta times the moment of inertia of the gate about the origin. Okay? So now we want, so this is the moment produced by integrating the net moments on all of these little differential strips of the fluid basically pushing down on the surface. And we've basically added up all those moments, and this here is that net moment. Now to find where to put the resultant force, we know the magnitude, and we just want to find where to put it. We want to find this y value of where to put it by basically setting f of r, this moment here equal to fr times yr. which is the same moment, which we basically need. So my based on the resultant force is equal to the resultant force times the y value, which is the moment arm. And we already found that the resultant force is just P naught times A plus rho g sine theta times the y value of the centroid. This here is just HC, but I'll leave it in terms of sine theta NYC times YR. Okay. So now we want this expression here, which is nothing more than the resultant force times the moment arm, equal to this expression here, which is the moment produced by directly integrating the pressure forces. Okay, and so we want them to be the same, and so we set my of our point load is equal to my from the integration. So this implies that P naught times area plus rho g sine theta times the y value of the centroid, times the area, times this times the moment arm for the resultant force is equal to the moment produced by directly integrating the pressure force. So that's P naught times YC times A plus rho g sine theta times IXX are the moment of inertia. So we can solve for YR. And when you do that, it's just algebra at this point. YR is equal to the atmospheric pressure times the y value of the centroid times the area of the gate plus rho g sine theta times IXX divided by the resultant force. Okay, this here is just nothing more than the resultant force. Okay, now there is a bit of a catch here, and we can fix that, and that's that this moment of inertia, which is here, is about the free surface. Okay, so I'm going to go up to the picture again. So the moment of inertia, IXX, is the moment of inertia about the free surface, which is kind of inconvenient. So it is normally more convenient to determine the moment of inertia about the centroid, because in the tables in your books and things like that, that is where in the tables in your book, in moments in statics and mechanics of materials, like the 1/12 BH cubed, those are about the centroid of the object. And so we need to move the moment of inertia from the free surface to the value at the centroid. Okay? And so recall the parallel axis theorem states that the moment of inertia about any is that you can that if IXX is with respect to 0, you can relate that to the moment of inertia about any point times the area times the y value of that point squared. And this is any y value. Okay, and so for this problem, or for these types of problems, it is most convenient to basically relate IXX to the moment of inertia about the centroid. So using the parallel axis theorem, we would use the moment of inertia about the centroid plus the area times the y value of the centroid squared, which we know. Okay, so then we have that the resultant force equals P naught times the y value of the centroid times the area plus rho g sine theta, it's a bad g, rho g sine theta IXX over the resultant force and that's equal to P naught times the y value of the centroid times the area plus rho g sine theta times the moment of inertia about the centroid IXC plus a yc squared. Okay, and that's divided by the resultant force. Okay. So I can simplify this a little bit. This will equal to P naught times area times yc plus rho g sine theta a yc squared. That'd be this term here, plus rho g sine theta times the moment of inertia about the centroid. And that's again divided by the resultant force. Okay. So I'm gonna group these two terms together here. So this equals, this will equal to P naught times the area plus rho g sine theta a yc times yc plus rho g sine theta ixc xc divided by the resultant force. Okay, and the reason that I left this in terms of the resultant force is because of a nice simplification, is that this term here is nothing more than the resultant force. Okay, and so this here is nothing more than the resultant force. And so this equals the resultant force times yc divided by the resultant force plus rho g sine theta times ixc xc over the resultant force. Okay, well here the resultant forces cancel out, and we just get that our final expression is that the y location of where to put that resultant force is equal to the y value of the centroid plus rho g sine theta ixc xc divided by the resultant force. Okay. And notice that this term here is always greater than 0. Rho is greater than 0, g is greater than 0, sine theta for our angles is always greater than 0, ix, the moment of inertia, is greater than 0, and because of how pressure works, is that we defined our force to be in the direction of pressure. Fr is greater than 0. So this entire term here is greater than 0. Okay. Which implies that the y location of where we put the pressure force, which is actually called the center of pressure, is greater than the y value of the centroid of the object. Okay, and the reason being, and so that means that if we go back up to our free surface diagram here, that if the centroid is here, we do not put the resultant force at the centroid like I have drawn. Instead, we put it at the center of pressure, and that's at some distance YR, which is the center of pressure. Okay, and the center of pressure is always deeper into the water than the centroid of the object. And the reason being is because the pressure is higher on the bottom of the gate than on the top of the gate. Okay, which basically means that that there's a net counterclockwise moment produced by the pressure about the centroid of the gate. And so to produce a counterclockwise motion, the resultant force has to be below the center of pressure. Okay? And so basically the center of pressure is always lower than the centroid for that reason. Okay? Okay. Okay, and so basically the center pressure is always deeper than the centroid value because pressure is higher as you increase y, or the depth of the water. Okay, and you can make a simplification to this expression here, although I prefer to use it this way, it's a bit more general, is that if the atmospheric pressure is 0, that means you are working in gauge pressure and not absolute pressure, then the resultant force is equal to P naught times the area plus rho g sine theta yc, and that means that this term is 0. Then that basically means FR is just rho g sine theta. So we have rho g sine theta here divided by another rho g sine theta there. And so the center of pressure then just becomes YR is equal to YC plus the moment of inertia about the centroid divided by oops, got an A here, forgot that, sorry about that, divided by the Y value of the centroid times the area. Okay, and so this also works, but if and only if the atmospheric pressure is taken to be 0 gauge pressure. Okay, if not, you have to do it this way. Okay, so now we will do an example. I'll go up to this page here in a little bit. So we'll do a little example just to show you how to apply this. So here we have a tank like this. There's atmospheric pressure on top, and we have a little circular gate here. So if we are looking at it from above, this here is just a circle, okay? And it's filled with a fluid, a water, that has a specific weight of 9.8 kilonewtons per cubic meter. We have a circular gate, and the diameter of the gate, oops, wrong one, is 4 meters, okay? And there's a shaft that you can use to open the gate, is at the horizontal diameter. Okay, so you could think of it as a butterfly valve. And the angle that this gate makes is 60 degrees with respect to the horizontal. And to keep the moment from trying to open the gate, there is a stopper here. So now what we want to find, if you want to design the pin, you want to know the resultant force that is pushing on the gate. And if you want to analyze how hard you're going to have to apply a moment to the shaft, is basically how much of a moment you need to apply to the shaft to open the gate, to basically counteract the moment that the water produces on the gate. Okay, and so we can do that. And so we're asked to find those two things. So when I do the problems, I like to find the properties, just to have them basically listed in one place. Then we know that rho g, which is equal, I don't know why the thing did that, we know that rho g is equal to the specific weight, and that's equal to 9.8 kilonewtons per cubic meter. And we know that for a circle, the moment of inertia is just pi r to the 4th over 4. And ignore that. I'll go over that theory here in a little bit. Okay, and so now we're going to go through the solution. Okay, and so first we might as well just find our area and our moment of inertia about the centroid, just for the sake of doing it and getting it out of the way. So A equals pi d squared over 4. Now, normally I prefer to work in symbolic form with these problems until the very end. These are some of the few problems where I don't like doing that just because the formulas become a bit ungangly and sort of cumbersome. But when we work with the Bernoulli equation and the control volume analysis, most of the time I will want you to work with the symbolic letters until the very end. But for these problems is our notable exception to that rule. Okay, so the area is equal to pi times the diameter squared, 4 meters, squared over 4. And notice I put the units attached to every single number. So this just equals 4 pi meters squared. Okay, and then the moment of inertia about the centroid is equal to pi over 4 r to the 4th, and that equals pi over 4 times 4 meters over 2, because that's the diameter, to the 4th power, and that equals 4 pi meters to the 4th. Okay, so we've just done our back of the envelope things to find the moment of inertia, which we're going to need, and the cross-sectional area. So now we want to find the resultant force that's pushing on the shaft and the net moment. So part A, we're to find the resultant force. So our free body diagram on the gate would look something like this. Our to find the resultant force would look something like this. We have a resultant force from the pressure pushing on it. And also we have this gate, it's on the side of a tank. So we have air on the outside of the tank. So not only do we have a distributed pressure load from the water pushing on the gate, but we have atmospheric pressure, a uniform load of atmospheric pressure pushing on the gate from the back. Okay, so we have resultant force from the water pushing on the front, and a uniform load of atmospheric pressure times the area pushing on the back. Okay, and the reason that we can assume, and technically there will be a very slight increase, a higher air pressure on the bottom of the gate than there is on the top. But the specific weight of air is about 1,000 times less than it is of water. And so the change of pressure here is infinitesimally small compared to that of water. Okay. Oh, and one thing I forgot to mention, I'm going to go back up to the picture, is that the height to the bottom of the gate, or to the center of the gate, is 10 meters. Okay, and we know that the centroid of a circle is basically at the center line. Okay, and so the shaft is at the horizontal diameter. Okay, so we got this little picture here. So now both sides will have atmospheric pressure applied, and you'll see what I mean when we basically work off with the equation. Okay, so we have the P naught on the top will be exactly canceled by the atmospheric pressure on the bottom side. Okay, and so we would have P naught times area pushing on the back, because we have we would have a uniform load of atmospheric pressure pushing on the back. Okay, so the resultant force equals P naught times the area. Here I'm just finding the pressure at the centroid is just nothing more than the pressure at the centroid. I'll actually do that. The pressure at the centroid times the area, and that gives the resultant force from the water pushing on the shaft. But we also have an atmospheric pressure load basically pushing from behind. So we need to subtract that out. So P naught times the area. So this would be the backside. and this would be the top side. Okay. And this term here is really the resultant force that we computed above. Okay. And so this equals the pressure at the centroid, which is P naught times the area, plus rho g times the height at the centroid times the area, minus P naught times the area. Okay? And so this term here is nothing more than the pressure at the centroid times the area. But notice that term has an atmospheric pressure. That is the atmospheric pressure that's pushing on the top of the water, is also added to the hydrostatic pressure that is pushing on the gate. And that is exactly canceled out by the atmospheric pressure that's pushing on the back of the gate. So these two go away. Then we now know everything. So this implies that the net force pushing on the gate equals, and this term here I should say is gamma times the height of the centroid, or the height at the centroid, times the area. Okay? So we want to find the net force. We know gamma, we know the height at the centroid, and we know the area. So we can just stick in the numbers. Then we get the resultant force is equal to 9.80 kilonewtons per meter cubed times 10 meters, because that's the depth of the water to the shaft, which is pinned through the center of the circular gate, times the area, which is 4 pi meters squared. And notice again, I have units after every single number. I expect you on your homework to show that. Okay. And this implies if you punch it into your calculator, you should give a resultant force of 1230 kilonewtons. Okay. So now for part B, we are asked to find what moment it would take to open that gate. Okay? So to do that, we know the resultant force of that is pushing on the gate. We know its value. Now we need to figure out where to put that, because essentially our free body diagram, which I should have actually drawn above, is that we have the resultant force from pressure pushing on the gate. We have a reaction force in the x direction. We have some weight of the gate, a reaction force in the y direction, and because we want to open the gate, we need some moment to actually turn and open the gate. And the minimum moment that it's going to take to open the gate is a moment that is slightly greater than the moment produced by the pressure loading. Okay? So first we need to find where to put this moment arm. Okay, so we'll go up and figure that out. Well, we know that that's at the center of pressure. So we need to find the center of pressure. So find the center of pressure. YR. Okay. And YR equals the Y value of the centroid plus rho g sine theta I xc divided by the resultant force. And that equals, well, we know from the geometry that the Y value of the centroid is going to be not this distance here and not this distance here. It's actually going to be this distance here. Okay. And so we know that the depth here is 10 meters. We know the angle is 60 degrees. And so this would be just RH divided by sine of theta. And so this would be where the centroid is. Okay? So that equals 10 meters over the sine of 60 degrees plus rho g, which is just gamma, which is 9.8 kilonewtons per meter cubed, times sine of 60 degrees times 4 pi meters to the fourth, which is the moment of inertia about the centroid of the gate, which is circular, divided by the resultant force, which is 1230 kilonewtons. Okay, and if we add this up, this term here gives us 11.55 meters, and this little addition here is 0.0866 meters. It's a really crazy Okay, so the center of pressure equals, if you add those up, it's 11.6 meters with respect to this to the liquid surface, or YR minus YC equals 0.0866 meters, and that's with respect to the centroid. Okay. So we know now where the center of pressure is, and it's just a little bit below. So if the centroid of the gate is here, it's just a little bit below the gate. So this distance here is 0.866 meters because YR gives us the distance from of the length of the moment arm about the free surface of the water. Okay, so YR is giving us this value here, or this value here, I should say. Okay, and so we just want, we're gonna take the moment, we're gonna turn the shaft, and we want to know how much of a moment it's going to take to open the gate. And so we are turning the shaft, and so we need to compute the moment about the shaft of the gate. Okay, so we just want to find the moment, so we have the resultant force, and we have the moment. And we don't know what the weight of the gate is, and we were not asked to find the reaction forces. So if we want to find how much the minimum moment is going to take to open the gate, we just apply static equilibrium and sum the moments about the centroid. Okay. So again, note that the shaft is at the centroid. Okay, so we sum the moments about the centroid, and that equals the resultant force times this moment arm here. So that's FR times the Y value, or the center of pressure, minus the Y value of the centroid, minus RM that is required to open the gate. And we're finding the equilibrium point because if we apply a moment that's slightly larger than that, we will actually open the gate. Okay, and so this implies we can solve for M. M equals the resultant force times the center of pressure minus YC, which is nothing more than the moment arm between the resultant force and the shaft. And that equals 1230 kilonewtons times 0.0866 meters, and this implies that the moment is equal to 107 kilonewton meters clockwise. Okay, and so that is